have a triangle where all the angles are the same. So if this larger triangle, it looks very similar in shape. If I tell you that this is also 20 degrees, that angle, and this is a right angle, then we know that this one here is 70 degrees. So we can say that these triangles have identical angles. They're called similar triangles. And similar triangles have great properties. It's almost like a ratio. You can see that here, the length of this one is 11 centimeters. And the length of this one just happens to be 33 because I'm really nice, but it could have been anything. It could have been 24. The ratio of 11 to 33 we get by taking 33 and dividing it by 11, and hey presto, it's 3 times larger. So this triangle has this bottom length here 3 times larger than this one. The great property of that is that means that this hypotenuse here is also going to be 3 times larger. It has to be, because the angles are identical. So this 12 centimeter hypotenuse in this triangle must be 12 times 3 equals 36 centimeters long. Okay, if I wonder then, well, what will the perpendicular length of this one be? Well, I can measure the large one. It ends up being 15 centimeters. So I know that this one has to be 15 divided by 3. So this one has to be 5 centimeters. Okay? So properties of similar triangles, when the angles are the same, the lengths are always a ratio to one another. What about this one then? Because these is actually put as 2 triangles, and we don't know whether they're the same. Well, we can see that they've both got a right angle. We can also see that they are intersecting lines. And one of the properties of intersecting lines is if this is angle alpha, then the opposite angle is identical to it. And we'll go through the properties of intersecting lines at the moment. So this must mean that these are similar triangles, because this angle here must be 90 minus alpha. And this angle here must be 90 minus alpha too. Because these 2 small angles here are alpha, the opposite ones must be 90. So we have 2 triangles with identical angles. So what can we say about the lengths then? Well, we can say that this length C divided by the other hypotenuse, let's put a little squiggle through it, we've taken this one. Which one is this one? This is the hypotenuse. Where's the hypotenuse on this one? It's upside down. It's actually this one. So C divided by L is going to be exactly the same as the ratio of this one at the bottom of the perpendicular sign is going to be the same as this one here. So we get equals B divided by M, which equals A, the last one, divided by K, the shorter length. So we'll get, this ratio is always true for similar triangles. So if we know 1 or 2 of the others, we can work out what the other one is. Okay? So 2 of one and 1 of the other, and that's enough to work out the other lengths. That's a very important property of similar triangles, and it doesn't matter. We could have actually, instead of drawing it like that, we could have just said, could have drawn it here as well, inside there. And we could have called this one, which one would have that been? It would have been M. This one would have been K. And this little one here would have been L. And then the whole one would have been C. And they can actually be quite often put inside one another like that. But it's exactly the same thing is going to happen anyway. They all share the same angles, and therefore they're all going to have this property that's true. The larger one divided by the smaller one will give you the ratio to either multiply or to divide by. So that's one of the things. Here, why then are these 2 angles opposite one another identical? If this is angle, let's call it angle A. What's this angle? Well, this angle is on a straight line. So this one here must be 180 minus A. But there's another straight line here. If I cover my hand over here, if this one is 180 minus A, what must this one be? This must be A too. because all the angles on a straight line have to add up to be 180. A plus 180 minus A gives us the 180 that we know has to be there. So these two must be identical. They must both equal A. And this one here must equal 180 minus A. What can we say about these type of angles then here? Well, let's call this one angle A. This one must be identical with this one. So we know that this one has to equal angle A as well. But these two lines are parallel, and this is coming down at a plane. So what is this angle down here going to be? It's also going to be identical to angle A, because these two lines are parallel. So this angle here actually just gets protruded down here. They're cutting at the same angle. This is one line cutting a horizontal line perfectly, and the horizontal. So if this one has angle A, this one has to be angle A too. And if this one is angle A, then this one is angle A too. So another way of thinking about it as, yes, you know, opposite angles like that are the same, but you can also think of it as angles with parallel lines in a Z shape or a backward Z shape. They're also going to be, A is going to equal A. So these opposite angles on parallel lines equal one another as well. So you've got some lovely properties of all these intersecting angles, and it's really your old 7th grade theory, and it's in the Formula 7 book. So if any of you'd like some practice on that or some questions on that, I can give you some pages from that book to repeat. Okay.